what we have done so far. So we have a function yx which minimizes this functional ju, that is when u is equal to y, j is a minimum. And now we are constructing functions ux by perturbing this by a quantity which depends on another function eta x, which is 0 at the two ends of the domain. So this function is arbitrary except for the fact that it's 0 at the two ends, and this ensures that any ux that we construct through this route by perturbing over the actual function that minimizes this functional, we will ensure that this function is always admissible. So now, since we know that this is ux is going to be equal to yx when epsilon equal to 0, we can immediately write that d epsilon of ju at epsilon equal to 0 will be equal to 0. This is my identity, and this identity can be written by expanding u in terms of its perturbed form, which is y plus epsilon eta, evaluated at eta equal to 0 equal to 0. So this is the identity that we impose in order to find the differential equation that governs y. Now we will use another way of writing this quantity we will define as the first variation of the functional j, and therefore this, which leads to the Euler Lagrange equation as we showed in the previous installment of this lecture, is delta j equal to 0. So equivalent way of writing the Euler Lagrange equation is to write delta j equal to 0. Moreover, we will call this eta first variation of delta y. So delta y is actually a function is identified with eta, and epsilon times delta y is a perturbation over y. So a perturbation of y, you can think of it as delta y. And what we are basically saying is that what is the delta y, what is the y which gives you delta j equal to 0. So this is called the first variation of j, and delta y is the first variation of y. Now so delta j, we have already seen, is a function of y, is a function of y prime, so we had earlier written this as del j del y eta plus del j del y prime eta prime. This is how we had written it, and now eta is identified with delta y and eta prime is with delta y prime. So this is how we write it, and we can write it in even a more succinct way, like del j del y prime times delta y prime, which we can write as del j del vector y dotted with delta y, where delta y is the set of all variations of the functions that j depends on. So delta y is the collection of functions on which j depends, which is y and y prime. So delta y and delta y prime is what delta y is. Del j del y with a vector y is a set of derivatives with respect to functions that j depends on. That is, this is del j del y and del j del y prime, and this dot product is what we can write it as. So from here you can see that delta j is actually the directional derivative of j in the direction of delta y. So delta y is an arbitrary direction that we have specified, and del j, del y are the derivatives with respect to y and y prime, the set of derivatives with respect to y and y prime. So what this thing gives is the directional derivative of j in the direction of delta y, and delta j equal to 0 gives me the Euler Lagrange equation. So this identity, instead of writing this identity in this manner, we write it as delta j equal to 0, where delta j is the directional derivative of j with respect to all the variables that it depends on in the direction of delta y. Similarly, we can extend this and calculate the second variation. We don't need the second variation in a course on linear finite element methods, but for a nonlinear finite element method we will use this. So it is dd epsilon of delta j evaluated at epsilon equal to 0 will give you the second variation of a functional in analogy with the definition of the first variation. So first variation is delta j equal to 0, del square j equal to 0 is the second variation. Now we can there are rules for doing this operation, and the rules are pretty similar to what you did for differential calculus. So if you try to take delta of two functionals, first variation of sum of two functionals, it is equal to variation of the first plus the variation of the second, or minus the variation of the second. Product of two functionals, variation of the product of two functionals, exactly the same way as you do for a differential operator. J1 by J2, same as you do for a differential operator. And there's a commutative property which comes in very handy, that is ddx of delta u. Remember, delta u itself is a function because we are using this as a surrogate for eta x. So ddx of delta u is delta of du dx. So this delta and this d can be commuted. Similarly, the delta can be taken inside and the integral sign, provided these limits are fixed. These are fixed limits. Then you can take the delta inside the integral sign and you get delta u dx. Okay, so these are the properties of the delta operator, and the Euler Lagrange equation is simply therefore written as delta j equal to 0, and delta j by definition is dd epsilon of j perturbed from the minimum function evaluated at epsilon equal to 0. So this has to be equal to 0 for this to be a minimum. This is the basic definition, and this delta operator follows these rules. Now, whatever we have learned so far can be very easily extended to more complicated functionals, say functionals of two dependent variables u and v, which themselves are functions of x and y, two independent variables. So I have a functional that depends on u, v, ux, vx, uy, vy. These are derivatives with respect to x, with respect to y, and so on. So I will now calculate this quantity. I'll now calculate the directional derivative of j in the direction of delta y, where y is the set of these functions u, v, ux, vx, uy, vy, which means delta y is delta of these. Delta y are perturbations of these functions, the set of the perturbations of each of these functions, and therefore del j del y will be written as del f del u delta u plus del f del v delta v plus del f del ux delta ux, and so on, integrated over the volume. This is how you will write delta j, and will set that equal to 0. Now let us take this, because we want to get rid of this derivative, so we will write it as let's write it here, del f del ux del delta u del x. This is what delta ux means. It's the x derivative of delta u dv. This is what I have as this term. Now I can write this as what I have done here. So I can write this minus del x of so if you take the difference between these two terms, this is what you will get. Now this, to the first term, I can apply the divergence theorem. So you have del x here, so you will get an nx, so it will become a derivative with on the boundary, and you will get del f del ux times delta u nx integrated over the boundary, minus this will remain a volume integral, which will be del x of del f del ux delta u dv. Now if you have u's and v's specified all over the boundary delta v, then obviously delta u is going to be 0 at the boundary. So this term is going to be 0. So this is what is going to remain. Similarly, from the next term here would be del f del vx delta vx, which you can treat in the same way. You will get minus del x of del f del vx delta v dv, and so on for all the terms. If you write the terms together and collect all the delta u terms and the delta v terms and all the surface terms. So I have calculated all the surface terms that I have got, and then delta u terms and delta v terms, and then apply so this has to be equal to 0. I again apply the logic that delta u and delta v are completely arbitrary functions of x and y, and therefore for this to be 0, for the volume integral to be 0 separately, the term inside the first bracket has to be 0, the term inside this bracket also has to be 0, and this surface term has to be 0 separately. So when this surface term has to be 0, again delta u and delta v are arbitrary, so this has to be 0 on the surface, this has to be 0 on the surface as well. So when you do this, you get the Euler Lagrange equation for the case where you have a functional of two variables of two independent variables. So the Euler Lagrange equations are these two. These two are your Euler Lagrange equations, and you get two sets of boundary conditions. Firstly, the essential boundary conditions, which are these. So when delta u and delta v are 0 all over the boundary, then these are the essential boundary conditions. In addition, we also have what is known as the natural boundary conditions, which means that this can be 0 and this can be 0. So the zeroness of this last term, the surface term, can be imposed if delta u and delta v are equal to 0, which would be the essential boundary conditions. They can also be imposed if the term inside these brackets are also 0. So these are not essential boundary conditions. These are called natural boundary conditions. So the natural boundary conditions come out of your variational principle. So when you minimize your variational principle, you get the natural boundary conditions, whereas the essential boundary conditions are built into the variational principle. So we not only get the Euler Lagrange equations, which are the governing equations that should be obeyed at each and every point in the body, we get the natural boundary conditions as well. Again, take a very small example. This is your functional u and v. U is a function. It's a functional of a single dependent variable, which is a function of two independent variables x and y. So this is your functional. Go back to this. So since it's a single variable, single dependent variable, we have to use this one. So your functional is ux square plus uy square. Use this one. Del f del u is equal to 0. Del f del ux is 2ux. Del x of del f del ux is 2uxx, that is del square u del x square. Similarly, del y of del f del uy is 2uyy. So this first equation becomes uxx plus uyy equal to 0, which is same as del square u del x square plus del square u del y square equal to 0, from which you have to find the function uxy, which satisfies whatever essential boundary conditions you specify on the problem. Now, this is the Laplace equation. This is the Laplace equation of the harmonic equation. So the harmonic equation, solving the harmonic equation, is absolutely equivalent to minimizing this particular function.